Good afternoon. Good afternoon. You are welcome again to our classes. This is the week 5th of our lectures. So uh, let me share my screen. So we shall be looking at analytical function this week. So, but before I proceed further, any question from the last classes, from all the classes we have had? If you have any challenges, come attention to it. We look at it together. I think last week I asked you to look at some of the TMES exercises. If you have done it and you have issues, can you please simplify it and let us resolve it amicably? Otherwise, we proceed to the next thing. Okay, it's like no more question. Okay, so today we shall be looking at analytical functions. So what are analytical functions? How do they look like? How do we solve them? How do we handle them? So these are the things we are going to be looking at today. So let's go straight to the course materials and start from there. So, like I said, we are going to be looking at analytical functions. So now, the question is that a function is f of z, a function f of z is said to be analytic at a point z naught if its derivative of f exists not only at z naught but at every point z in the neighborhood of z naught. So what I'm trying to say here is that if you have a function and you take the differential or you find the derivative of the function at a particular point called z naught, and you have a result for that function, then the function is said to be analytic, not only at that point, but at some point very close to that point you have considered. So that leads us to, let's say for example now, we have just discussed U and V plane some last week. So let's say we have U and V plane that consists of X and Y. Now, if you take second derivative of U with respect to X, the result should be the same thing as taking derivative of V as with respect to X and Y. The same thing, if you take derivative of V with respect to Y and X, you are still going to have similar things. So in a nutshell, we can say that the square U the X square plus the square U the Y square is equal to 0, meaning that the two of them are equal. One will be in positive, one will be in negative. By the time you put them together, the result will be equal to 0. So we say thus the U of xy and V of xy satisfy Laplace equation, and this is what we call Laplace equation. This equation is the Laplace equation. So if you have a function and you take the derivative of the function and you substitute it inside the Laplace equation and it gives you 0, then automatically the function satisfies Laplace equation and it is what? Analytic. So let's look at, there is a law that says if the derivative of f of x exists at a point z, then the partial derivative of u and v exists at that point and obey the following condition. Another condition is this. We have just looked at one. This is one, which we call the Laplace expression. That is, we take the partial derivative twice. So now let's say we just take it once. How does it look like? The u dx is equal to the v dy, and the same thing, the u dy is equal to minus the v dx. So this equation is called Cauchy-Riemann equation. So if you have functions and you take derivative and the result is analytic and you put it in this expression, then if you satisfy this, what we call Cauchy-Riemann equation, the function is what? Analytic. So now let's look at Cauchy-Riemann equation now. A necessary condition that W is equal to f of z is equal to this be analytic in region R is that U and V satisfy Cauchy-Riemann equation. That is, if you are given a function and the function you want to test if the function is analytic, it must satisfy what we call Cauchy-Riemann equation, which is this. So let's look at view example and see how these things can be looked into. Now look at this and see that show that f of z is a closed set which is defined by this. That is, f of z is equal to es to the power of z is analytic in this, and that the ez, the z is equal to this. What we are trying to say is that we want to check if this function is analytic. And how do we know if it's analytic? It must satisfy Cauchy-Riemann equation. Now we know that z can be written as x plus iy. So if z can be written as this thing, so what we just need to do is just to substitute this here. Then we have our f of z to equals to this now. So if we expand this now, in law of logarithm, we can say that this which is plus can go to multiplication. Then you have ex eiy to be this. So if you express this further into complex plane, the whole of this, look at this, the whole of this one is this in complex plane. So we now have ex to equals to this. So if you expand this now, you have two terms, ex cos y and ex sin y, which satisfy u of xy and v of xy condition. Now the next thing is to now differentiate this. Take the partial derivative once and take the partial derivative of this once as well, to now see if the two results we are going to obtain will satisfy Cauchy-Riemann equation. So the first thing is that du dx, x is here. If you take the derivative of this, a constant, you still have us then cos y. If you take the u dy now, is by the time you take the cos of this now, it will give you negative sign. So you have this. Do the same thing for v now. You have this, the v dx of this will give you this, and the v dy will give you this. So now let's see if this satisfies Cauchy-Riemann equation. Cauchy-Riemann equation say that the u dx is equal to the v dy, and the u dy is equal to minus the v dx. So now this our du dx, es cos y, if you put it here, which must be the same thing as the v dy. You see that this and this are the same thing. This expression and this expression, the two of them are the same thing. So that's satisfy one condition. The second thing is that the u dy, which is this, must equals to minus the v ds. This is the v ds, they're negative, they are the same thing. So by solving this now and satisfying this, the function is said to be what? Analytic in nature. So the next thing in the question is that, hence, if f of z is this is analytic, then we show that if we take the derivative of this now, we are going to have e to the power of z. So now we have just expressed this now, that is f of x is this and this, which is e cos y plus height. And so if you take the derivative now, it will be du dx plus dv dx. So what is our du dx? Our du dx is this, which is this, and our dv dx, this is our dv dx, is this. By the time you do the algebra and put things together, you have this expression, which technically satisfy and reproduce this result, which is so automatically the derivative of this is equal to this. That is how to solve the problem in this case. Any question? Any question on this? Any questions? Okay, if you don't have any questions, I think we are good to go for this week. So we are stopping the class there for this week. So next week we will be looking at complex integral. Please look at your notes, go through it before the next class, because we are very close to the end of the lectures, and by now you should be getting set to write your exams and all these things. So if you have any questions, you are free to contact me by emails or by text messages or by sending messages to me on WhatsApp. Thank you very much for coming for the lecture. See you next week.